And thank you for coming one more time to hear me speak. I hope you're not too bored of me. I'm very glad to be here, and it's been a great trip. I'm going home tonight, but everything was really great here. So thank you all very much for the food and the places to see. Everything was great. So I'm going to talk a little bit about towards a Nielsen theory. So this talk is all mostly kind of ideas, which I think are probably correct, but maybe not everything. So this is, I said last time, everything will be a conjecture that I'm talking about here. The first thing that I told you all about a few days ago was the Nielsen theory, fixed point theory, and then the next thing I talked about was digital topology, and today I want to try to talk about some kind of combination of the two. So we want to try to do a homotopy invariant digital fixed point theory, and this has not been done before, as far as I know. Until recently, I thought it was impossible. Actually, some people have tried to do this, but there were some serious problems, and I always thought that this was not possible. And people would ask me, "Here's a tweet. Stop asking me about digital Nielsen theory. It can't be done." It's from June last year. Actually, this is not a real tweet. I just made this up right now. You can see 390 likes. No, there's not 390 people who would like this tweet. Yeah. Also, my name here is not Nielsen Boss. It's not my Twitter name. But anyway, I used to think it's not possible, but I changed my mind about that. The two things that I didn't know about before, and I do know about now, are called strong homotopy and cubical homology. And these are both new ideas from the last year or less, which I think are really important ingredients that we need these things in order for the digital Nielsen theory to work. So before I thought it wasn't possible, but now I'm beginning to change my mind about that. So the main thing we want to compute, as usual, is the minimum number of fixed points when you change the function by a homotopy. And that means, I'm going to say a little bit more about what exactly we mean by homotopy, but you should feel like it means just change the function in a continuous way. As I said last time, I think actually it's more likely that we want to talk about approximate fixed points, not actual fixed points, because there are many things for digital images where the actual fixed points don't behave very nicely, but you can say more about approximate fixed points. So probably the second one is the more likely thing that we're going to study. And I said before, this had been tried before by these Turkish guys. I don't know how to say Ege and Karasa, I think. But there were some serious mistakes, errors in what they were doing. And this, like I said, I thought it was impossible to fix, but I think maybe we can. So let's talk about homotopy. This is the picture of a classical homotopy. It's when you have a function and you change it in a smooth way or in a continuous way, like this. And the fixed points move around a little bit. This is a classical homotopy. This is not digital. This is a smooth, function, continuous function. What about this? When you do digital homotopy, it looks more like that. You have the points which are connected by adjacencies, and the points just move one at a time. You can move more than one point at a time, but they move one position each time. So this is what a digital homotopy looks like. So we want to know what can happen to the fixed points when you do this to the function, change it in this continuous way. Continuous meaning you don't break these lines. They always stay adjacent to each other. Points move in discrete steps. They move only to other adjacent points. That's what, and they never break the adjacencies. That's what I said. So this is what a digital homotopy looks like. Here's the definition. I know I didn't say the definition of homotopy last time. It's not very clear, actually. It's kind of complicated. But we say F is homotopic to G. That's what this means. When there's some interval, the interval is like, you should think of like the time. The function is changing over time. And this is the time interval. You start at time 0 and you go up to time k. And there's some big continuous function like this, x cross the interval to y, where these the following. There's going to be three things here. They're all true. So this says when the time is 0, you have the first function. And this says when the time is k at the end, you have the other function, g. So you start with f and you end with g. And then in between, this function is continuous in x. That is, for each fixed time, when you change the x, it's continuous. And also, it is continuous at t. For each point x, the homotopy function is continuous in the time. And if all those three things are true, then we say it's a homotopy from f to y. So this is what I mean by homotopy. It means f is continuously changing step by step until it becomes y. All right. Instead of the second two things here, continuous in x and continuous in t, you can just say this. It is continuous with the product. This is how you do it in classical topology. This, if you want to say it this way, you have to use the appropriate adjacency in the product. Remember, every digital image has its own adjacency relation. And if you use the correct adjacency relation in the product, then it's equivalent to all of these things that I set up there, the more complicated definition. Actually, there's two different ways you can make it adjacency, and this is something that Sirajo mentioned in one of his presentations. Two different ways to make an adjacency on the product. One which allows no diagonals between the two factors. This product has two factors, and you can consider adjacencies with diagonals or without diagonals. And the one which allows no diagonals, that has a name, is called NP1. These names are from Boxer a couple of years ago. And the one which does allow diagonals, so no diagonals, NP1. Yes diagonals is NP2. All right. And the definition, this means actually there's two different kinds of homotopy you could use. You could use a homotopy using no diagonals, which is the NP1, or the one using diagonals. The one that I said before is actually the one which uses NP1, and that's called homotopy. If you use NP2, that's called strong homotopy. And this is a new thing, which I wrote a paper about this, and it's not published yet. So this is a brand new idea. It's easy to show that if you have a strong homotopy, then it is also a digital homotopy. That's why it's called strong. It turns out you could also say it this way. A strong homotopy is one which changes only one point at a time. In that example of the function changing, you saw sometimes more than one point was moving at each step. Strong means that you can do it using moving only one point in each time step. All right, for example, this one right here, if this is my digital image, the cycle of 4 points, the square, here the identity is homotopic to this projection. This is when you just make everything go down to the bottom. The 2 points up there go down. And if you do that in one step, move the 2 points down in one step, that is homotopic to identity because you just moved 2 points by one position. So the identity is homotopic to this projection, but it's not strong homotopic. You have to, if you want to move these points down, you have to move both at the same time. If you move only one, then the adjacency across the top will be broken. If I move only this left point down one and keep this one where it is, this adjacency will get broken in the move. So the identity is homotopic but not strong homotopic to this projection map, because you have to move 2 points at once. You can't do it using moving only 1 point at a time. This distinction between regular homotopy, strong homotopy is not well studied at this point because it's a brand new idea. But I think it's important, and it's definitely important in what I'm about to say for the rest of this fixed point theory. All right, so let's try to make some kind of Nielsen theory. In Nielsen theory, if you remember from last time, or even if you don't remember, it's okay. There are two ingredients. One is the fixed point index. You can't see very well, but remember there's a way to make a number for each fixed point. Depends on how the graph is crossing the diagonal. So when the graph is going down, that's a +1. When it's going up, that's a -1. That's the fixed point index. And then the second ingredient is this picture. Also hard to see, sorry. This is the fixed point classes. You group the fixed points together according to whether these kinds of paths can exist. If there's a path from one to the other that is homotopic to its image under the function, then they're in the same fixed point class. All right? These are the two ingredients in Nielsen theory. The idea is, let's talk about the index first, right? Every fixed point carries a number which is preserved by homotopy. Actually, this does not work, as you're going to see, for digital images. This is not going to work very well. Here's an example. So in dimension 1, like the domain here is dimension 1. This is what a +1 fixed point looks like. The graph goes down through the diagonal. Digitally, it would look like this. If I try to just copy this picture, the graph goes down through the diagonal, okay? That would be a +1. But what happens if I change this by a homotopy? How about this? You can change, if I just push this up a little bit, it will become this. And now there's no fixed points. Remember, the index is supposed to be the same when we change the function a little bit. The fixed point moves a little bit, and it has the same index, +1 or -1. But here, this fixed point did not move a little bit. It's completely disappeared, all right? The fixed point is removed here. So you could say now it's an approximate fixed point, but we converted. We had one fixed point before, and now it's two approximate fixed points, which is a little strange. And it's not clear what should you say is the index. If I have two fixed points now, two approximate fixed points, is it like 1/2 each? It's not clear what it should be. Or check this out. You could change it in another way. What if I move it up like this? Now I had one fixed point, but I change into two fixed points. And again, it's not clear what should happen with the index. None of this kind of thing can happen in a classical topology unless the index was 0. Then everything can be 0. That's okay. But this is very strange, and it's not clear what to do. So my own opinion about all of this, I believe there's no index of a fixed point in the digital setting. At least I can't think of a way that this can make sense. If we want it to be homotopy invariant and additive, then we also need to count approximate fixed points. But even so, it's not clear how to make the definitions. So probably it's impossible. That's just my own opinion. So really, we are not going to talk about the index of a fixed point, which is a major obstacle. And this is why I thought for a long time that this was impossible, because if there's no index, then it's very hard to create the rest of the definitions for the Nielsen theory. But anyway, let's try something simpler. This is, let's talk about the Lefschetz number. So this is the definition of the Lefschetz number. I don't know if that looks simple to you, but it's this trace with the alternating sign, the trace of the homomorphisms in homology. This is complicated, and you need to do some algebraic topology to compute this in the classical setting. But actually, in the digital setting, this is not very complicated at all. And we're going to do some very specific examples. And if you are paying attention, you could do all the examples yourself. You don't need to know anything special to do this. So I want to copy the Lefschetz number in the digital setting. We have to use, I will just mention, digital homology groups. They have been defined before by other people. These are some of the same, one of the same Turkish guys that I mentioned before. They define the digital homology groups. Here's the basic idea. If you know something about homology, it's the same idea as ordinary classical homology. But even if you don't, it's a simple idea. These, we call them the standard simplices. In dimension 0, it's a point. In dimension 1, it's a line segment or an edge. In dimension 2, it's a triangle. In dimension 3, it's this tetrahedron, and so on. So each of these things in each dimension is some kind of version of a tetrahedron. If you want the definition, this like delta Q would be a set of Q plus 1 points, which are all adjacent to one another. So these are the standard simplices. And we're going to, when we talk about the homology, we're going to look at how these things are embedded inside X. So what kinds of things are inside X? Here's a very simple example. If we have this square here, we have 4 0 simplices. Remember the 0, dimension 0, that was just a point. And there's 4 of them. Those are the vertices. And we have 4 dimension 1 simplices. Those are the edges. There are 4 of each. All right? This is what the homology is about. It's about how many of those things are inside the space. And we want to talk about, if we have a continuous function, how will those simplices move around? And it's not hard to do this. Actually, these movements can be described by matrices, which you can write down very specifically what they are. Here's an example. You have to make a name for everything. So I call all these points x0, x1, x2, x3. And then the edges, I'll call them E0, E1, E2, E3. And you have to make orientations on the edges when you do this, but it's not hard to do. It doesn't matter how you choose the orientations, you just have to be consistent. And for example, let's talk about a function here. I'm going to do a horizontal flip. So it just exchanges the points from left to right. So f of x0, this point goes to x1, and x1 goes to x0, and then these two, they do the same thing. So we just flip horizontally. All right, I would like to know how can we describe the function in terms of the simplices? Well, this right here, I've told you exactly what happens to all of the dimension 0 ones, all the points. What about the edges? You can, it's not hard to say, you can compute the function on each one-dimensional simplex, the edges. F of E0 is this edge. When you do the flip, it's still E0, but it's backwards, the reverse orientation, and you write that as minus E0. So the minus means that it's going to the opposite orientation. And you can just think about all these other ones. This edge here goes to the other side. Oh, this should say minus, sorry. E1, when I flip horizontally, becomes minus E3 because it goes over here, but it's pointing the other way. And then f of E2 is minus E2. And f of E3, again, this should be a minus E1. E3 goes over here, but it's the opposite direction. All right. I wrote F1 here. This means f in dimension 1. That's the dimension 1 behavior of f on the one simplices. All right. And these, I said before, you can make a matrix out of these. So the first ones, this is what happens to the points, dimension 0. And then dimension 1, this is what happens to the edges. And we make matrices out of those. All right. So this f of x0 equal x1. The first column is x0. The second column is x1. And you just put these into a matrix. You see some of them had minuses, so they have minuses over here. All right. These are called, the name for these matrices, these are called the induced homomorphism on the chain groups. Technically, this CQ of x is defined to be the abelian group generated by all dimension q simplices. And the induced homomorphisms always look like matrices, and they're always easy to find. You write everything down and you can find these matrices. All right. So here's I say conjecture. Sirajo will prove this sometime. Maybe already did. I don't know. Tonight, maybe? By the end of this week. Okay. Digital Hopf trace theorem. All right. In classical topology, the same thing is called the Hopf trace theorem. It says, when you add up the traces of these things in the homology, you get the same answer as when you add up the traces on the CQ. All right. Why this is important? Because this one over here is easier. It's the one I was just talking about, those big matrices. The other one, you have to, is not much harder, but you have to understand something about the homology groups to do this one. And that's harder. So this one is easier. That's why we want to prove this theorem. The trace in homology is the same as the trace in the chain groups. That's called the Hopf trace theorem. All right. So what that means is, remember, this equals the Lefschetz number. This was the definition of the Lefschetz number. It means instead of using the homology, when you do Lefschetz number, you can use the chain groups. And it's much easier because you don't have to do the homology groups. All right. So if the Hopf trace theorem is true, then the Lefschetz number can be computed simply as the sum of these traces. So in our example here, this is easy to do. You just do the trace of the matrix. In our example, it was like this. These were the two matrices, and the Lefschetz number would be the trace of this one minus the trace of this one. You do minus because the sign alternates in the sum. And you just add up the trace. The trace here is 0. The trace here is minus 2. So the Lefschetz number overall is 2. All right? These are very simple computations to do. Any questions about that? I hope it makes sense. All right. In classical topology, I mentioned this before. If the Lefschetz number is not 0, that means you have a fixed point. Actually, that's not true in digital topology, but something like that will be true, but not exactly a fixed point, because the Lefschetz is 2. All right. In the digital setting, this is the appropriate fixed point, and this also Sirajo will prove this one. Maybe not this week. I don't know. We have a lot of things to prove. This is like the Lefschetz fixed point theorem, but digital version is if the Lefschetz number is not 0, then f has an approximate fixed point, right? The classical version doesn't say approximate. It just says then f has a fixed point. But in the digital image, you need this approximate. So that means f of x may be not equal to x, but it's equal or adjacent to x. That's what we mean by approximate fixed point. All right? And this, you could call this the digital Lefschetz fixed point theorem or Lefschetz approximate fixed point theorem, something like that. Abdullahi fixed point theorem? I don't know. Yeah, okay. Here's the a brief question about the Lefschetz number. Here, question, why should we even use the Lefschetz number? Those matrices are so easy to construct in any example. The F0, the first one, is a matrix which tells you exactly what happens to all the points. So when you do the trace of that one, actually it equals exactly the number of fixed points. So if you know this matrix, you already know the number of fixed points. So why do you need the Lefschetz number to tell you about fixed points if you already know about fixed points? The interesting thing is that, yeah, what is the Lefschetz useful for if we already know the exact number of fixed points from the dimension 0 trace? What's useful is that the homotopy properties. So because of the Hopf trace theorem, this sum of the in the chain groups is the same as the homology groups, but the homology groups preserve properties with respect to homotopy. So the sum in the homology is invariant under strong homotopy of the function. And this is why the Lefschetz number is interesting, not just to count the number of fixed points. The trace of F0 is not invariant under homotopies, but the Lefschetz number is invariant under strong homotopies. So the Lefschetz is more useful than just a trace because Lefschetz number tells us about all maps which are homotopic to the original function, not just about the original function itself. Okay, anyway, in this example we had the Lefschetz equals 2 of, remember the function was the flip horizontally. That means any map which is strong homotopic to F has an approximate fixed point. That's by that Lefschetz fixed point theorem. Here's another example, same set, but this time I'm going to do a rotation by 2 positions. So f of xi equals xi plus 2, where you read mod 4 in the index. So x0 goes to x2, x1 goes to x3, and so on. Rotation by 2 positions, all right? Again, it's not difficult. We can compute these matrices. You just have to think about where does all the points go and where do all the edges go. The matrices look like this. You can find the Lefschetz number by adding the traces. You get 0 both times. Both traces are 0. And so, since the Lefschetz number is 0, we cannot conclude anything about the approximate fixed points. Remember, the theorem says, if the Lefschetz is not 0, then you have approximate fixed points. But here, the Lefschetz is 0, so we don't know if there is or is not an approximate fixed point. Actually, if you just look at this, you can see there are no fixed points and also no approximate fixed points. So it's not a surprise that the Lefschetz number is 0. All right? Excellent. Yeah, in fact, there are none. There are no approximate fixed points. Here's a bigger example. Can we do it even in a larger set? Yeah, we can. It's not difficult. It may take you a few more minutes to write down what the matrices are, but it's not hard. In this case, I'm going to consider a rotation, just the whole thing, just turn it over, 180-degree rotation. What does it look like? Well, if you could do this yourself, take a few minutes and write down all these matrices. It looks like this. All right, these are the matrices that you get, and then the Lefschetz number. We add up the traces, so that the trace of this first one is 0. This one is -1. So we add them in this way. You have to alternate the signs. And we get 1, which means any map strong homotopic to F has an approximate fixed point. All right? This is pretty easy, I think. It's not hard to make the computations. Very easy for a computer. Even if you have a very big digital image, you can do this without a problem. If you're using a computer, certainly this will be easy. Actually, you don't even really need to label everything. You don't even need to find the whole matrix. Here's an example. Oh, not yet. The trace, remember, the trace of F0 would be how many fixed points there are. Something is on that diagonal of the matrix when it maps onto itself. So the trace of F0 is how many fixed points. The trace of F1 is how many edges go to themselves. You have to remember the signs. It could be +1 or -1. But these traces you can find even if you don't know the whole matrix. Here's an example. So this is workable even in very big examples, like this one. It's my favorite example. Usually this has the legs, but I took away the legs because the legs are disconnected and it makes everything slightly weird. But I took away the legs. And I also made the arms go the same way. That's because I want to do, my function is going to be a horizontal flip this way. So the arms have to go both down. Now, there are no vertices, no points are fixed by this flip, which means the trace of dimension 0 is automatically 0. You don't have to write down the whole matrix. You can say immediately, the trace in dimension 0 is 0. What about the edges? In dimension 1, there's 4 edges here that go to themselves. And those are the only edges that go to themselves. Those 4 right down the middle. And each one is being reversed because you're doing the flip there. That means this trace is -4, right? Because there's 4 of them. There would be -1 each time in the matrix. Like I said, you don't have to make the whole matrix. You can think about this without writing down the whole matrix. So when you do Lefschetz number, I go 0 minus -4, which is 4. And so it means any map strong homotopic to F has an approximate fixed point. It's pretty good, right? I think so. One more big idea, and then, yeah, when we did the chains here, the simplices, we use triangles, right? Recently, within the past year, this is the other idea that I didn't know about before, but has come up recently. And this was not my idea, but some people have experimented with other shapes, not triangles, but you can do the same idea using other shapes. And here's a preprint. It's not published by Jamil and Ali, not this Jamil. These are, yeah, and not Aliyu. These are 2 people in Pakistan, in Karachi. Samira Jamil is a woman, I think, and Danish Ali. Anyway, they use cubes instead of triangles. You can do it. Why would you do it this way? I don't know, but you can do this instead of triangles. Use cubes. So they use the cubes, and they call their theory is called cubical homology. The other one is called simplicial homology. You use triangles. They use cubes. It's called cubical homology. We can do all the same things using cubes instead of triangles. So the simplicial looks like this, triangles. The cubical looks like this, using cubes. You should notice in dimension 0 and 1, they're the same, right? There's points in dimension 0. In dimension 1, they are edges. But in dimension 2 and higher, they're different. Let's see what we get here. If we are doing cubes now, we have 4 vertices and 4 edges, just like before. Now, in the simplicial, the triangles, there is no dimension 2 triangle here, or any higher dimension. But there is a dimension 2 cube. So even for this simple example, you should expect there's a difference between the simplicial and the cubical. They behave differently. Right? A 2-dimensional cube is a square, which is the whole thing. There is one square, all right? So if we use cubes instead of triangles, we got 4 in dimension 0, 4 points. 4 in dimension 1, that's 4 edges. And 1 dimension 2, 1 square, all right? And let's try and do the same thing. So we label everything, the points, the edges, the cube I call Q0. Because there's only one of them, all right? And if, again, we consider, I want to do the same example, the flip, a horizontal flip, back and forth this way. Here's what the matrix looks like now. In dimension 0 and dimension 1, they're the same as before, because 0 and 1, simplicial is the same as cubes. But this time we have a dimension 2 cube, and it is -1 because Q, when you flip it, goes to itself, but in the opposite orientation. So you have to think about the orientation in dimension 2 is a little bit different, but it works. So the matrix in dimension 2 is just a single 1-by-1 matrix, has -1. Anyway, now when we do the trace, the Lefschetz number, it's different, right? Here I'm going to call this the cubical Lefschetz number. So this is the same thing, but you use cubes instead of the triangles. And when you add it up, this time you get 1. So Sirajo is going to also prove a lot of things about cubical Lefschetz number. All right. It has slightly different properties with the homotopy and with the approximate fixed points. So this is it's interesting to me. In classical topology, we have only 1 Lefschetz number, but in digital images, it seems like there's actually 2, and maybe there's others with some other shapes I don't know about. But it has so there's a simplicial Lefschetz number and cubical Lefschetz number. Some of the properties of the cubicle are better and some are worse. One better one is that the cubicle is homotopy invariant. The other one was strong homotopy invariant. This is better. Any homotopy invariant. This is something that Jamil and Ali figured out about cubical homology. This is, in my opinion, this is why cubical homology is so good for digital images. It's fully homotopy invariant, not strong homotopy. All right. Actually, this has nothing to do with fixed points, but you can actually use these two Lefschetz numbers, either one of them, to show that two maps are not homotopic. For example, on this example, remember this? When we did the Lefschetz number here, we got 4. If you do the cubicle, no, sorry, I'm not going to do the cubicle. Let's just think about, what if we use the identity? What is the Lefschetz number of identity? When you do identity, those matrices, when you draw them, they are always the identity matrix. So the trace is just how many points there are. There's 34 points here. And this trace is how many edges there are. And there's 36 edges here. And so the Lefschetz of the identity in this example is -2. Whereas, remember, that flip had the Lefschetz number equal 4. What that means, since these Lefschetz numbers are different, it means automatically F is not strong homotopic to identity. That's because the Lefschetz number is preserved by strong homotopy. All right. So since they have different Lefschetz number, they must not be strong homotopic. And this actually, if we do it using cubical, we get this for the cubical Lefschetz number of the flip, and this for the cubical Lefschetz number of the identity. Again, they're different, which means they are not homotopic, because if they were homotopic, they have the same cubical Lefschetz number. So you can use the Lefschetz number to prove that these are not homotopic. This is something, I don't know if that's impressive to you, but actually this is hard to show otherwise. To show if I just give you two functions and I ask you, are they homotopic or not? It's not easy to answer that question. But the Lefschetz number is one way you can use to show that two functions are not homotopic. Especially on a big example like that big PAPI thing, it's not easy at all to show that something is or is not homotopic. Okay, all of this was just the Lefschetz number. I'm getting near the end. I hope it's not too long. What about the Nielsen number? I said I wanted to talk about towards Nielsen theory. The Lefschetz number is one step. Can we do the Nielsen number? Remember, the Nielsen number must involve what we call the fixed point classes. Sorry, this is hard to see again. 2 points are in the same class if you can make a path from one to the other, and then the image of that path is homotopic to the original path. I'm going to give you a very vague description of how I think you can do this in digital images. We're going to do something like what I called last time the Reidemeister trace. I just want to do it for this example to give you the basic idea. We're not going to do anything very specifically. So this digital image and the flip, all right? Remember, when we do the Lefschetz number, we do these traces. In dimension 0, there is nothing because there are no fixed points, no vertex goes to itself. And in dimension 1, we had these 4 edges, which were all -1s because they're being reversed. So the trace in dimension 0 is 0. The trace in dimension 1 is these numbers, which adds to -4. The -1s come from these edges, which are being fixed, but they're being reversed, which is why it's -1. We can do something here that's similar to the fixed point classes. So what we're going to do, like for these 2 edges, I would like to know, can these 2 edges, the approximate fixed points, somehow be combined by a homotopy? I'm going to take a path from here to here. Let's call this one alpha. And you look at the image of that path, f of alpha. It would be over here, right? That's because when I do the flip, if we start with this path and you flip everything, it goes over here. And these 2 paths, the alpha over here and the f composed with alpha, they are not homotopic because there's a big hole in between them. You can't move this one into the other one because they are, the mouth here is a big empty space in the image. They are not homotopic, and so these approximate fixed points cannot be combined by a homotopy. All right, this is the basic idea that we do in Nielsen theory. I think it can work just the same way in digital images. So these cannot be combined by a homotopy. For the ones up here, though, maybe they can, because if you say take these two edges, the lower two from the above the mouth, then you can make a path here, which is alpha, and the f of alpha is over here. And now they are homotopic here. There's no empty space in between them because they're right next to each other. So this means maybe those two approximate fixed points can be combined. That's the idea. Or those four. There's four of them. All right. Remember when we did the Lefschetz number in the dimension 1, we had these all -1. What we can do if you want to do something like a Nielsen number, if you use the Reidemeister trace, you get something like this, where one of them is different from the other three, right? One of them is down here, and it cannot be joined with the other three because of this big hole in the space. And so the way that will look, if you write down this weird trace, it looks like this -1 is this one right here, the one on the bottom, and then the other three go together. And this A represents the loop around the mouth. So this is saying we have one that's kind of below the mouth, and then there's these three, but to get to those other three, you have to go around the mouth to get to them. All right, this is called the Reidemeister trace, and this can also be computed as a trace of a matrix. We're still going to have the trace 0 in dimension 0, but the other one looks like this weird thing, -1 -3 times A. So when you add up the whole all the traces, you just add these together, just like in the Lefschetz number. What you get is this. You end up with one thing and then 3 of another thing. And what that means is we have 2 different classes of approximate fixed point. There's the one which is the 1 and the one which is the A. These 2 different classes cannot be removed or combined with each other. And so we're going to say the Nielsen number is like 2. And that means that the minimum number of approximate fixed points, it must be 2 or more, right? You cannot ever get down to only 1 because of they're separated by the mouth in this example, all right? Actually, I think in this example, the actual minimum number you can get is 8, but I'm not sure about that. So this is not the best possible way to measure the minimum number, but I think it's pretty good though. This will take a lot of work to make all of these definitions correct and to prove all the theorems. I would say you should ask me about it in a year and I will tell you how it goes. That's how long I think this might take. All right, that's all. Thank you very much.